So welcome everyone. Thank you for coming. I hope the lunch isn't going to make you a bit too drowsy because this is a bit of a dry paper at some point. But yeah, so hello everyone. I'm presenting my work on mesh contour extraction. And so what's mesh contour? Well, to simplify, we want to find the silhouette of a mesh. So this is useful for a lot of applications like shadow volumes, magnetic sampling, differential rendering. But me, I'm mostly interested in stylized rendering, especially line rendering. And this can be used to achieve high quality styles, like the one on the left from Grabli and colleagues, which one is from 2010. This is only a 3D render with the lines. And you see it's also a very useful field application, as a lot of games are into styles that use a lot of lines. For instance, anime style, like in Guilty Gear Strive, where being able to control the thickness of the line and have them be pretty is a big part of the appeal. So what's exactly mesh contours? Well, if you take a look at the diagram on the right, the idea we want exactly is to find the frontier between the visible and invisible parts of the mesh. So, which means the front faces and the back faces. We want to find the edges between the two. As you can see on the camera, you only see this silhouette, this contour. The mathematical definition is quite easy. You take one edge, you check the two normal vectors, and if one of them is looking towards the camera and the other one is looking away from the camera, that means you got a contour. But there's a slight precision, is that the view vector must be recomputed for each edge because we are in a perspective projection. This is important for a bit later. Yeah, so of course we could try to do a brute force algorithm where we check every edge on the mesh, but meshes have a lot of edges and therefore it's a bit too slow for video games, you know? Like if you say 2 milliseconds to a technical director, he's already looking at you pretty weirdly. He doesn't want to do that. So, but thankfully, contours, there are not actually that many of them, you know, like about 30%. So we could use some culling approaches. Like if I look at you from the front, like my torso, the middle of my torso isn't going to be a contour. We can safely discard it. So that's what we did. As you can see on the left, we have our mesh with all the edges colored in. While on the right is the actual result we want, the mathematical result of the contour. And in the middle, this is after a curling pass. This is the only edges we test. So we already eliminated quite a bit of them, actually. So, of course, there is previous work on the subject. Some of the methods used hierarchical culling, which works pretty well to eliminate a lot of edges, and works mostly on CPU, which is a problem because we kind of want to go on GPU a lot to be fast. But GPU implementations, well, they don't really do culling, they just do brute force. So what we propose is a flat patch decomposition, so it can go very well on GPU, for mesh contour extraction. So this talk is going to be separated in two parts, like the method. The first one is going to be on the pre-computation steps, like how we are going to make our patch decomposition, and the second one is going to be on the real-time results once we get into it. So the idea of this is to group edges into patches that we want to curl, that are worth curling. So if we imagine a function E for expectancy that measures the expected computation cost of a patch, and by that I mean the computation time, we want to find a set of patches that minimizes the total execution time. So this has two questions. One of them is how to compute said patch decomposition, and the other one is how can we estimate this function E. So let's start with the first one. It's going to be simpler that way. Because we can't actually find the ideal set of patches, because that will be like exponential in complexity, we use a greedy bottom-up approach. Every edge is going into a separate patch, and then we try to fuse these patches together at each step. We look like, yeah, if I fuse page A and B, will it be faster in the end? And so we use this gain formula. And then at the end, we also do a final pass to see if the patch is better just being computed every time in brute force, or if it is actually worth it. So let's take a look at it visually. Let's start with a simple mesh, you know, tetrahedron, 6 edges, easy. So we cut it into 6 patches, each one with 1 edge. And then we compute every possible fusion between them and their respective gain. And then we look in that whole table and we see, yeah, this one's the best fusion. So let's do that one. And when we do that, we then, we discard the previous results, as you can see in the red squares, and we recompute the new fusions possible with this new patch. And we continue this algorithm until there is no more gain to be made. And so, well, of course, you can see that you can think about, does it scale? Like we are computing every possible thing. And the answer is no, because it's actually cubic in the number of edges. That's why you can, however, partition the mesh into groups. We did 4K edges. So this removes some tests, so you're not sure to have the optimal solution. You will lose a bit of precision. However, we found out that it was quite manageable into our tests. And each one of these groups can be computed in parallel and has a fixed time or around the same time for each group, which means this problem becomes linear in the number of edges. We also have an issue with memory because you have to store all the fusions, of course. However, so this one's a bit technical, so it's just in the paper, but we found a way to make it linear once again using a small cache that holds the best fusions for each patch. So we saw how we make the decomposition. So now let's get into the mathematical part. How can we estimate the computation cost? So let's first take a look at our data structure. So which we took from Johnson and Cohen's 2001 paper. So this one is composed of two things. There's the bounding sphere that holds all the bounding sphere, all the edges, not the faces, the edges specifically, and a normal cone which encompasses all the normals of the faces of the patch. So, and once you have that, when you want to use it, you can then compute with the camera position the view cone that will hold all the possible view directions for that. And that means that our actual idea here is that because we want to see if you can have a contour on each side of the view direction, basically we want to see if are the view cone and the normal cone perpendicular to each other. If they are, there might be a contour. But if they are not perpendicular, we can curl the patch safely. So that's the idea. But how can we find then how many times this patch will be curled? So that's the idea. If we start from that formula for the test formula, which simplifies to that. So it's actually if is the normal vector in that perpendicular to that cone, which we can actually switch up, like what is the perpendicular projection of a cone on the sphere? That will be a spherical bend. Like if you try to take the cone in your hands and move it around, rotation, that's gonna be a bend. So, and the idea is we want to check how many times we can curl the patch over all the possible view directions for a fixed camera distance, Dcam. So that means we want to integrate over a sphere. So we do the ratio of these areas, so the spherical band over the whole sphere. And this gives us a very simple formula, which is just sine, actually. And so that means that with that, this is heuristic function h, we can say, for instance, yeah, this patch will be curled 80% of the time. So from then on, we add a calibration step where we compute where we measure the computation time of a single patch and the computation time of a single edge. And we put the expectancy function at the time it takes to compute a patch plus the time it will take to compute all the edges of the patch times this heuristic. So if you are computing if you are curling the patch 80% of the time, that means we're only going to count 20% of the time for the edges, as it's the mean one, the mean time. So of course that means we have a calibration step that changes by machine, but the actual in the paper you can see that the performance isn't impacted that much in the end, just about 5%. So that's useful but not critical. So from then on, we also had a small addition to this. So instead of taking the bounding sphere, which bound the whole patch geometry, if you remember the definition we said earlier, we only need, we did a new view vector per patch, but it can be any point, not only on the edge, but on the straight line bound from the edge. Therefore, if we want a volume that intersects all these lines, that means it can be outside of the bounding volume and still work. Of course, this volume is quite hard to compute, to compute the optimal one. Yeah. So what we do instead is that we only take the midpoints of this, which allows us to speed up the algorithm compared to the bounding sphere one, actually. But we also we also have a smaller sphere, which is about 20% smaller. So we get that additional extra percentage on top of it. So, and we wanted to test this and to find out if it was actually useful in practice. So we did tests on 10 models in 3 categories. So we have static objects, you know, the first 4 ones. We have environments, and we have rigged characters. With edge counts, they change between 60K to 7.5 million for the statue. We also remove the rigid concave edges because we are going to compute only the visible contours. So that's a previous result. And for rigged models, which is actually a useful use case in video games, especially because you usually want to make outlines around characters, we actually separate them into rigid parts based on their bones. So like my arm is gonna be only computed with the arm, like a separate model than my forearm. And all the parts that are dependent on 2 bones, like the elbows, are going to be recomputed every time as if using a brute force algorithm. We are comparing our method with SNCH because we took their own structure, and with Mesh Optimizer for the GPU version, because Mesh Optimizer does meshlets for the GPU, which is a close application, but as we will see, it isn't actually made for the problem. So there are some, we'll see the impact of that. So in terms of pre-computation time, so we have in general, compared to SNCH, we have a generally similar pre-computation time, but we have a much smaller number of nodes because of their hierarchical nature. I'll bring your attention to the Armadillo model because it's actually quite representative of AAA quality models. Like it's about the same poly count as Lihiron from Immortals Phoenix Rising, which did release not that many years ago. And compared to Mesh Optimizer, they tend to have a bit more patches than us, which means that we end up with larger bonding spheres, but our own normal cones are smaller to compensate. This is a visualization of our method compared to Mesh Optimizer. The colors of the edges are colored along for each patch. So as you can see, Mesh Optimizer, because it's made for meshlets, all their patches are contiguous in space. Ours hasn't got that limitation, so it can find edges that are a bit further away, but that would go better together. As you can see, like our kerning is a bit less dense. It works a bit better if you take a look visually. And for rigged models, like it depends a lot on the way your model is weight painted. For instance, like on the left, you have models that are more organic, so we can only optimize about half of them, which you can see a bit like the torso of the pigman is a bit higher, or Gawain's head, he's bald, he has so he doesn't move much. You can optimize a lot of it. But on the other end, you have the Tuba Gunner, which is mostly a rigid model because it's like a robot. This one we can optimize a lot more. So let's get into the actual results themselves. So this is the real-time part. So what we did for test procedures is that we did 252 renders. So they're all made on a sphere, to have equally spaced viewpoints. And we did that at 6 instances, some that are closer than the one we optimized for. On the CPU, we do that sequentially. On the GPU, we estimate all viewpoints at once. And that's not scientific, but I actually made a lot of implementations to find which one works faster, with the buffer order, all of that. So even the brute force is quite fast. So in terms of CPU, let's start with the percentage of tested edges. So in red is our own algorithm, while in black is SNCH. And as you can see, we don't test our rig models and don't handle them properly. But as you can see, we tend to test about the same number of edges. They do a bit better than us on object, a bit worse on environments. So you will think the performance would be similar. However, because we are actually a flat structure, we don't need to go through as much patches and patch tests, which means our algorithm is always faster than SNCH and is actually 2 to 5 times faster than the brute force algorithm. And unfortunately, SNCH is not adapted to the GPU. So once again, of course, here, by the way, it's relative. We compare to the performance of the brute force because the times can be quite different between each model. So the pink line in the middle is the time it would take as a brute force. You can see sometimes it even takes longer. So as you can see, testing the least edges possible is not always the best solution. And when we go to the GPU this time, Compared to Mesh Optimizer, once again, we find out that we are getting better results. Once again, about 2 to 5 times faster than brute force for our method. However, and because there you can see that Mesh Optimizer is not really tailored to that problem. Like they reason in faces for starters and not edges, which means that the patches are not always the best for this task, and this highlights the need to have a specific algorithm. As you can see, the times are quite stable even with the different points of view, and we get some really nice times actually. Like on my 1080 GPU, I'm getting 30 microseconds for one model, for one AAA model. So our technical director is going to be very glad that it can now fit inside of it without breaking the budget. And yes, so we also did two pipelines in Vulkan in order to test it in another context. And we did find out that the compute shader version was faster than the task or mesh shader, which would seem like a counterintuitive reason, but in the end, because we curl a lot of edges, a lot of the tasks we send are actually going to be empty work groups. So we lose a lot of time on the empty work groups, which means that the computer implementation does perform a lot better in the end. Yeah. So to wrap it up, so we did make a new method for fast mesh contour extractions with time gains that are critical for video games, because we can now use it without battling for 2 years with the rest of the team. And we also opened up some new research directions, like with especially for tighter bonding volumes. Like as you can see, we use the simple method, but finding this smallest sphere is still an open problem, especially if you want to do it fast. Some ideas could be applied to other curling applications, especially like the idea of the heuristic function. I could see that being applied to backface scaling, for instance. We didn't do any tests yet. And rig characters, well, they still remain a bit challenging, like even if they are being computed faster, like, although we don't handle any of the mixed parts like the elbow and stuff, we actually don't think that's gonna be like, there's a big gain to be made here. That's why we didn't search for it. Like if you remember the formula, it's a sine. And because you want to do that very fast, if you were to estimate like the new normal cone and bonding volume, you're probably gonna overestimate. And because it's a sine function, as soon as those two cone angles will get a bit bigger, you're gonna lose performance quickly. So we don't think it's gonna be worth it. However, we didn't actually go into that direction, and because it's such an important use case, I believe that could be interesting to look forward to. And yeah, so thank you everyone for listening to the talk, and I'll now field your questions if you have any.